Okay, so now that we know how to find derivatives of simple polynomials, like the one we see here, we now want to talk about how to evaluate a derivative. In other words, give it a value. And we can't do that unless we have a point that we're given to explore. So in this case, we're going to be looking at the point when x is equal to 1, and we're looking at this function, which is a second degree or a quadratic function. Now, x equals 1 is just a number that I chose. I could have chosen x equals 5 or negative 2. I'm just picking a point that may be of interest and exploring what's going on there. And we'll look at the picture of this here in a minute, but just keep in mind there's nothing magical about x equals 1. So when we talk about evaluating a derivative, there's basically 3 steps. The first one is to find the general derivative of the function. In other words, find f prime of x. So we're going to ignore the x equals 1 part for now, and we're just going to ask what is the derivative of f. And we know from the power rule that this particular function has 3 terms, and so we can apply the power rule to 2x squared, and then the linear rule to negative 6x, and the constant rule to 5. So the derivative of this function is just 4x minus 6. So the 4 is coming from the 2 times 2 on the first term. X is raised to the first power because we reduced the power by 1. Negative 6x is like a line with slope equal to negative 6. So the slope of negative 6x is negative 6. And the slope of 5, because it's a constant, is 0. So this is what we call the general derivative, f prime. Now this tells me everything I need to know about how f, the original function, is changing. We'll see how in a minute. So that's the first step, find the general derivative. The second step is to plug in or evaluate that function, the new function f primed, when x is equal to 1. That's what it means to evaluate a derivative. So we take f prime at 1, we plug in 1 wherever we see an x, so 4 times 1 minus 6 is 4 minus 6, which gives me negative 2. And so the last step is to interpret the meaning of that number. Now technically, we've evaluated the function when we get the number negative 2. But we want to make sure we understand what that means. Now, for a moment, just before you go to the next slide, before you click that next button, just pause this for a second and see if you can visually picture what that negative 2 means. Now keep in mind, the derivative tells you the rate of change, which is the same thing as telling you geometrically slope of a tangent line. So you may want to pause before you go to the next slide to see if you understand this. If not, you'll see it in the next slide. So here's the interpretation. What you see here is the graph of the function f of x. It's a parabola that opens upwards. And what I've done here is I've identified where x is equal to 1. And if you draw a tangent line at that point, then the derivative value that we just got, which was negative 2, is the exact slope of that line. So the exact slope of the line is equal to negative 2. So there's no estimation going on here. This is not like topic 3 where we were getting an approximate value of the slope of the tangent line. This is the exact slope. And it actually took mathematicians a very long time to figure this out, and a very long time to prove to themselves and to other people that this worked without any error whatsoever. But this is indeed the exact slope of the tangent line when x is equal to 1. Now, one of the powers of the general derivative f primed is that it works for any point whatsoever. You don't have to find a new derivative when you specify a new point. So if I change my mind and I want to look at x equals 3 instead of x equals 1, that's easy to do. You can see the picture here. At x equals 3, I've drawn a tangent line. And I want to know what the slope of that tangent line is. And so the general derivative of that function is still 4x minus 6. It has not changed. So if I want to find the slope of the tangent line, the instantaneous rate of change at x equals 3, then all I have to do is evaluate that derivative function when x is equal to 3. And so that's what I do here. 4 times 3 is 12, then 12 minus 6 gives me 6. So at that particular point, x equals 3, the slope of that line is exactly 6. So not only am I getting an exact value for the slope of the tangent line, an exact value for the instantaneous rate of change, but I'm also doing so in a very efficient way because that one derivative does the job for any point that I care about. So if you compare this to what we did in topic 3, as soon as I changed my point with the forwards-backwards method, for example, I had to completely do a whole new set of calculations. I had to evaluate the function going forward 1, then I had to evaluate the function going backwards 1, and then I had to do a slope calculation. Very tedious. Here, the formula in this case is actually simpler than the original function, and it's very easy to plug numbers into this. So this is the power of calculus. It's giving you very efficient and very accurate results with relatively little work.